Hello, this is Dr. Chad McGee again, and we're going to do some more quantum physics. Today's lecture, we're going to look about beta decay and all the peculiarities that happens with beta decay and actually how that relates to the physical geometries of beta decay. All right, so first off, let's look at our nuclear equation. When you have a neutron that does not have a correspondence with a proton nearby, it will undergo a decay, T1/2 equal to roughly 15 minutes. Okay, so we all like to call this the free neutron. Essentially, what happens in that, as we've discussed earlier, is remember a neutron has all paired momentum vectors. So there's none of them that has a net directionality vector overall. And because of that, light energy wants to make something so that it does have a light momentum vector. In this particular case, it will actually go through a process by which it breaks apart a piece of it and we make some new particles. And so in this process, you go from a neutron to a proton and a W- boson. Now, I drew this in brackets because the W- boson has a half-life in the order of 3 times 10 to the negative 25th seconds. So very quickly, this guy is going to go into making 2 more particles. You're going to have an electron and an anti-electron neutrino. Okay, so let's look at the geometries of what I propose these particles look like. We've already discussed the neutron having 3 sets of paired momentum vectors. Now, my take-home from this is in this process to do the formation of protons, one of those vector coils pulls off. Okay, so what we're going to have, and the net effect from that is one that has a net momentum vector. Remember, these are spin paired. Okay? These ones over here, 2 of them are spin paired, 1 is not. Now, this is a fun one. Okay? This one leads to being some tricky, what's the geometry of this? Well, it took me a little while to kind of think this out, but I think I know possibly what it might be, and that is this. Okay? Now, this is asymmetric. It does not have the symmetry to where one lobe's different than the other. Okay? One lobe is much greater than the other, and there's going to be a breaking point. And it turns out right here is this instability point. And once that breaks, we are now going to have our electron and a little bit of leftover energy, okay, momentum vector, that becomes the anti-electron neutrino, or electron antineutrino, I guess you would call that. That's a piece of antimatter. Okay, so this is the geometries of it, and then essentially you could think of the mechanism as one loop pulling off. You end up forming this guy. This guy is very unstable. Remember, 3.0 times 10 to the negative 25th seconds is very quickly going to make an electron in an anti-electron neutrino. All right. Now, that's fairly familiar beta decay. Correspondingly, you can do the antimatter forms of this. For every matter form that you would have, you do have an antimatter component. So the net effect from this is if you take an anti-electron under the same conditions, free, which means it's not tied to a net momentum vector from an antiproton, it should also have a T1/2 of 15 minutes. So the half-life from that guy should be exactly equal to that of a normal proton. Okay? The big difference is in the particles that we're going to make. with this process, which it's going to try to alleviate the spin pairing total, we're end up going to make a antiproton. Okay, so remember, the antineutron is going to be exactly spin paired like the neutron, except the directionality vectors are going in opposite directions. So we have 3 sets of paired, okay? In the antiproton, we've got 2 sets that are paired, 1 set that is not. So this pair and that pair. So we do have a net directionality vector, and it's exactly opposite of the proton one. And that leads to why this guy has a positive 1 charge, this guy has a negative 1 charge. Okay? Plus, we're going to end up with the W plus boson. Now, that of course is going to very quickly want to decay 3.0 times 10 to the negative 25th seconds and make a positron plus an electron neutrino. All right, so what's the geometry on this guy? Well, that's what I propose it. It's exactly like the W minus boson, except the directionality vector is opposite. Okay? And it's got a breakage point too. All right? So if that breaks at that point, you're going to end up having a positron form, and there's your electron neutrino piece. Okay? So the net effect is the momentum, the mechanism for doing the neutron should be exactly the same for the anti-neutron. It's just the directionality vectors are all flipped. Okay? Now this leads into something quite interesting. And that leads into the talk of the Z particle. I like talking about him. Why? It's a special case. This guy, it's its own antiparticle. So what could the geometry of this one actually be? Well, when I was thinking about this, it dawned on me it'd have to have symmetry. And so basically, it would look like very much like an infinity symbol, except we'd have a directionality vector enclosed in there. Now the nice thing about this, yes, it does have a breakage point in it, but this lobe and this lobe are exactly equal to each other. So if by happens to a decay process, what you would end up with potentially would be this. So potentially, if you had the right type of Z particle, the right energy, you could theoretically make an electron and an anti-electron, which then could go on to do an annihilation of it. Okay? But I'm not saying that necessarily all Z particles do have that property. But I'm saying that if you broke it at that stage, potentially you could have this. Now, what's interesting about this piece, this geometry, this and this are exactly the same. Okay? Consequently, because of the symmetry effect, yes, this allows for it to be its own antiparticle. So in the net effect, that is answering its own question. How can it do it? It all boils down to symmetry. Without the supersymmetry that it has, it couldn't be its own antiparticle. That's why the W plus and minus, W plus minus, do not have that. Okay? You actually do have a big difference between the W plus and the W minus, and that has to do with the lobes. They don't have the same symmetry. Okay? So at this stage, I'd like to give you an opportunity to digest that. So I think we're going to take a break and move on to another video. Keep thinking quantum physics.